Guess it's time to start. So today's speaker is Vijay Higgins at UCLA. He's going to speak about Skein identities at roots of unity.
Yeah, thank you very much for having me, hosting me here on this visit. So I like to talk about Skein identities in the Kauffman bracket Skein algebra. So I'll tell you what that means. And this is joint work with Indraneel Tambe, who's a PhD student at UCLA. So we'll recall the Kauffman bracket Skein relations, which are used to define an invariant of framed links. And so if you have a link diagram, then you can impose these two relations so wherever you see a crossing, you can replace your diagram by a linear combination of two diagrams where you resolve the crossing, either the vertical resolution or horizontal resolution. And then once you've gotten rid of all the crossings, you'll have loops. And then you can use this relation to remove any loop that bounds a disk. And then once you're done applying these relations until you can't anymore, you'll have a Laurent polynomial in this variable. And so these Skein relations are applied recursively. So if you have the top link here, you can first apply the crossing relation to this crossing and get this linear combination. And then you'd have to keep on going and apply the relation to this crossing on this diagram and that crossing on the next diagram. Keep going, but it eventually terminates for a link diagram in the plane. And it's an invariant of framed links instead of ordinary links. So for a framed link, you want to think of it as a union of embedded annuli. And so the only difference between framed and unframed is, in this case, we don't have an ordinary Reidemeister 1. Because if you think of that as an annulus, you want to think of it as a ribbon. And if you have one sort of kink in the ribbon, then you can't straighten that. But if you have one kink and then an opposite kink, then you can straighten that. So if you try this relation with a belt or something, then you'll see that this relation holds. And then you have Reidemeister 2 and then Reidemeister 3. And so since you can apply the Kauffman bracket relations to both sides of each of these relations and keep applying it until you can't apply it anymore, and both sides will reduce to the same thing. And so, since the Kauffman bracket respects these Reidemeister moves, it's an isotopian variant of framed links. And so what we want to do is actually use these Skein relations to define Skein modules of three manifolds or Skein algebras of surfaces. So it's using the thing that you build a invariant of links out of to construct other algebraic things using these Skein relations. And so, so this is just a little bit of context for, we'll talk about these being the SL2 Skein relations and what that means. So these Skein relations actually come from a quantum group denoted by UQSL2. And locally tangled diagrams correspond to morphisms in the representation category of that quantum group. And that the Skein relations correspond to relations among the morphisms. So there's a way that you can diagrammatically study the representation categories of quantum groups. And if you pick the quantum group associated SL2 to study, the Kauffman bracket relations are the relations that you get. And we'll talk about this a little bit more precisely later, but this is just for context. And then you can look at more complicated quantum groups than SL2. And for those, tangles aren't really enough to give you all of the morphisms. You need more complicated things like graphs with vertices, and those are called webs in the literature. And so Kuberberg sort of originated that study for the rank 2 Lie groups, SL3, SV4, and G2. And then it's hard to actually generalize it to higher rank. It took a while for SLN. In 2014, they figured out all of the relations that you would need, the analog, the Kauffman bracket relations that give you a way to describe the representation category of UQSLN. And then that was, their proof was sort of specific to SLN, and then it took longer for people to move outside of type A. So it's still an active area of research. So webs won't show up too much in this talk, but it's sort of my main area of study. So I'm sort of revisiting studying SL2 with an eye towards webs. Okay. So yeah, so we can use the Kauffman bracket Skein relations to build a Skein module. So you can take an oriented three manifold, and you can consider the vector space spanned by isotopy classes of framed links in that three manifold. And then you can impose the Kauffman bracket relations. So locally inside of a three ball, if you see a crossing, you can replace that with this linear combination of resolutions. And if you see a loop that bounds a disk, you can get rid of that loop and pick up the scalar along the way. And there's no, here there's no notion of when are you done simplifying, because crossing in a three manifold, the crossing is sort of a matter of perspective. If you look at it differently, it might not look like a crossing. So three manifolds are actually really hard to study using the Skein module, but it automatically gives you a three manifold invariant that you assign a vector space to the three manifold, and this is clearly a vector space, and it seems interesting, but it's hard to compute. But for Skein algebras of surfaces, so that's in the special case that your three manifold is just a surface cross an interval, then you have a projection onto the surface. So you can talk about link diagrams now on the surface, whereas in a three manifold, a link diagram isn't a thing that you can consider. But in a thickened surface, you can consider the diagram of a link on the surface. And you also get a nice, a natural multiplication, because if you have two diagrams, so here's a knot on the torus, and then here's another knot on the torus, and you can multiply them together by stacking in this way. And then you can extend that definition linearly or bilinearly. And you get an associative product, and it has a multiplicative unit as the empty link. And so, so you can build the surface this way, and then and now there is a way of knowing when you're done simplifying, because you have link diagram on the surface, so you can get rid of all crossings and get rid of all loops that bound disks. So, yeah.
Can you use the stick instead of the pointer? Because
It's too
the Zoom audience.
Will I be able to? Yeah. Oh no. I'll try to point. Yeah, so we can get rid of all of the crossings and all of the loops that bound this on the surface. And so you get an automatic spanning set of diagrams that don't have any crossings and don't have any trivial loops. And that turns out to actually be a basis. So you can prove that by using something called the diamond lemma. So, so you get a basis for free for Skein algebras of surfaces. And this parameter Q, we can choose that to be any invertible complex number. And the choice of that is going to influence the algebraic structure. And it sort of, so when you set Q equal to 1, then this Q to the 1/2 is going to equal Q to the minus 1/2. So both these coefficients are the same. And if you look at the other crossing, you would be switching Q to 1/2 to Q to minus 1/2. So if Q equals 1, then the overcrossing is equal to the undercrossing, and that product becomes commutative. So it's just a commutative algebra in that case. And it's actually the same thing as the algebra of functions on the SL2C character variety. But if Q is generic, if it's not a root of unity, then the thing you get has the only things in the center are the things that you would guess. So the empty diagram is in the center, it's the multiplicative identity. And if you have a surface with boundary, if you have a loop that's parallel to the boundary, like a loop around a puncture, that you can shrink that to bubble past any other element. And so that'll be in the center. And you got the whole center this way when Q is generic. But when Q is a root of unity, there will be surprising elements in the center that you wouldn't have just guessed would be there. And so that'll be related to the main point of today's talk is Skein identities involved with what happens when Q is at a root of unity. And so in the literature, the center of the Skein algebra is studied using Frobenius homomorphism for Skein modules. And so one goal of today's talk will be to give a new way to see that a Frobenius homomorphism is well defined. So how do we construct it, and how do we show that it's well defined? I lost the click.
Your stick can touch the screen.
But does it move the next?
Huh?
What do you mean it can touch the screen?
Yeah.
Is it supposed to?
I think you're trying to, use the shadow of the stick.
Uh-huh.
I think it's harder to.
Oh, yeah.
Yeah, just be closer.
All right, so yeah, so you've probably already seen some Frobenius homomorphisms in other situations. So in the classical setting, you're looking at a commutative ring in prime characteristic. And in that case, you can define an endomorphism of that ring by just taking, defining it on any element by raising that element to the pth power. And that will be a homomorphism. And it's due especially to this property that if you take a plus b to the p, you have to expand it out and you get these binomial coefficients. But in this characteristic, all of the intermediate binomial coefficients are 0, and you're just left with the extreme terms. And so so that this homomorphism respects addition. And then in the situation that's more related to where we are, we're not in prime characteristic, but we have some parameter q. That's our root of unity. So in this case, it'll be an nth root of unity. And so if you have in a situation where you have an algebra generated by two variables, and those two variables q commute, then you can define a Frobenius homomorphism. That's not an endomorphism of the ring. It goes from the q equals 1 version of our algebra to the root of unity version of the algebra. And then you don't take arbitrary elements to a power. You just take these two generators. You define it by raising these generators to the nth powers. And this will also be a well-defined homomorphism. And it's due to this Frobenius property that it doesn't hold for arbitrary elements. It just holds for the two generators. If you take x1 plus x2 to the nth power, you get x1 to the n plus x2 to the n. And if you wrote this out, these don't commute, so you don't get a binomial expansion, but you get a q binomial expansion. And in that case, all the intermediate terms, q binomial coefficients vanish in that case. And one thing to notice is that the image of this map is central, because if x1 and x2 q commute, then if you have x1 to the nth power and you multiply it by x2, you'll pick up one power of q every time you slide over, so you get 10 powers of q, and q to the n is 1. And so we get you got actually the whole center this way. So for Skein modules or Skein algebras, we want to consider an analog of this to construct central elements. And we want it to be a homomorphism. And we want to think of it as raising generators to powers. So in our situation, knots are generators of the Skein algebra. But I have these in quotation marks because we won't actually just raise it to a power. We'll do something slightly more complicated than raising it to a power. Okay, so that's the goal. So yeah, so I'm going to tell you what I mean by raising a knot to a power. So we want a map that goes from the q equals 1 Skein module to the root of unity Skein module. And we want it to satisfy the Skein relation so that it'll be a homomorphism. So if we look at the easiest Skein relation, that was the loop equals negative q minus q inverse. When q equals 1, that's just saying that the loop equals minus 2. And so if we want that to be if we want the Frobenius homomorphism to respect this relation, we need to send the loop to something that also evaluates to minus 2 when q is a root of unity. So when q is a root of unity, our loop value is minus q inverse. So q then equals 1. We apply the Frobenius to the loop. We better have it equal minus 2. And in this case, q then equals 1. So we could rewrite minus 2 as negative q to the n minus q minus n. And so we're trying to raise q to a power, but q doesn't really show up in the Skein module, where we can only apply an operation to a loop. So we need to actually view this as an expression and this as a variable. And we know that it's actually a polynomial. So this minus q to n minus q minus n is a polynomial in minus q inverse. And the polynomial that we'll use, we'll talk about it more later, but it's this nth Chebyshev polynomial that has the property. We can view minus q as an eigenvalue of an SL2 matrix, then minus q inverse is the other eigenvalue. And so this property here is saying that if you take the trace of an SL2 matrix and you plug it into our polynomial, you get out the trace of the nth power of that SL2 matrix. And so here, we're assuming that n is odd for this slide, so that minus 1 the n is minus 1. Okay, so from this computation, we see that it's reasonable to expect that we should be replacing a knot with some sort of polynomial of the knot instead of just a power of the knot. So I want to explain how to replace knots with polynomials and knots in general. So we're starting off with a framed knot, and we have some polynomial, and I want to tell you how to thread a polynomial along that knot. But I have to tell you how to thread a monomial along a knot, and then we'll extend that linearly. So if you have a monomial like x cubed, you look at your original knot, and you just take 3 parallel copies of that original knot. So for any monomial, you just take, so it's x to the I or whatever, and you take I parallel copies of the knot. And it's in the direction of the framing. So this is different than taking the power of the element in the Skein algebra, because we're just taking parallel copies. And this uses the fact that our knots are framed knots. And so, so to thread a monomial along a knot, we just take the corresponding number of copies of that knot. And if you thread a polynomial along a knot, you'll have the corresponding linear combination of knots that corresponds to threading each monomial along the knot. And if you have a link, you can do the same thing to each knot in the link. And I'll have that an example in the next slide. But are there any questions before we go to the example? Right, so if your polynomial is x squared minus 2x, and our link is the Hopf link, and we want to thread the polynomial along each component of the link, then it's sort of like multiplying polynomials. If you multiply these two polynomials, you'd have 4 terms, and one of the terms would be one x squared here and x squared here. So that's this. We have 2 copies of the first knot and 2 copies of the second knot. And then another term will be x squared times minus 2x. So here's an x squared and a minus 2x. And then here's the other mixed term, minus 2 times x squared times x, and then plus 4 times x and x. So that's how you thread a polynomial along a link. It's just, you sort of just, I guess each knot sort of should have its own variable. You should think of it that way. And then you can just multiply the polynomials together, and then whatever polynomial you have, you break it into monomials, and you reconstruct the links from that. Right, so we had seen some, there was a special polynomial involved with our computation of figuring out what we should do with the Frobenius of a loop. And so that polynomial was this, was Tn in that case. So there will actually be 2 Chebyshev polynomials that show up in the talk. So one of them is the Tk and the other one is Sk. And so the T polynomials are the Chebyshev polynomials of the first kind. And the S polynomials are Chebyshev polynomials of the second kind. And they have integer coefficients, and you can define them recursively using the exact same recursive relation that the kth polynomial is x times the k minus first polynomial minus the k minus second polynomial. And then the first polynomial is just the variable x. And but then the only difference is that the 0th polynomial for the T polynomials is 2, and the 0th polynomial for the S polynomials is 1. And so here you can think of it as if you take the 0th power of the identity, or the 0th power of an SL2 matrix, you get the identity matrix, and the trace of that is 2. So, so that's why there has to be 2. And then I guess we'll see from down here why the S's should be 1. S0 should be 1. So, so these satisfy defining properties involving the quantum integers. So here our quantum integer m is defined to be the Laurent polynomial given by this expression. And that if you expand this as a Laurent polynomial and plug in q equals 1, you just get back the original integer, the classical integer. So that's why it's called a quantum integer. And the T polynomials satisfy the property that Tk of q plus q inverse is q to k plus q to minus k. And that's that same property of that this is Tk of the trace of an SL2 matrix is the trace of the kth power of the SL2 matrix, if you think of q as an eigenvalue of an SL2 matrix. And the S's satisfy a more complicated relation where if you plug in quantum 2 to the Sk, you get out quantum k plus 1. And these end up being the quantum dimensions of irreducible representations of UQSL2. And so, and we can depict these polynomials diagrammatically. So in the annulus, so we talked about how there's a standard basis for Skein algebra of a surface. If your surface is the annulus, you get rid of all crossings, all loops that are trivial, and then the only non-trivial loop is one as a core loop of the annulus. And so you think of the core loop of the annulus as a variable, and so all the irreducible diagrams will have to be copies of the core loop, which are just powers of the variable. And so you'll get that the Skein algebra of the annulus is just a polynomial ring in one variable, and that variable is the core loop of the annulus. So if you have a diagram of the annulus, it'll evaluate to a polynomial. This box is the Kayth Jones-Wenzl projector that I'll define in a few slides later. But yeah, so if you close up that particular element, you'll get some polynomial, and it ends up being this SK polynomial. And if you know some representation theory, this corresponds to the Kayth irreducible representation, or the irreducible representation of pi suite K. And this guy is the character polynomial of that representation. And then the T's also have a diagrammatic description, but only when Q equals 1 does this picture work. So here you take a knot and you just wind around the annulus K times. And if you're at Q equals 1, then if you evaluate this in the annulus, you get exactly this polynomial here. And you can prove that by looking at the outermost crossing. You expand that, you'll see this recursive relation show up. Okay, so yeah, so are there any questions? So I haven't told you what Jones-Wenzl K is, but I will soon. Okay, and I guess this picture is also related to taking the, if you think of a loop as an element of the fundamental group, then if you concatenate it with itself K times, you get this, something that's homotopic to this guy. And so that's related to why you're getting the trace of the power of a matrix. So we talked a little bit why that Tn is important for root of unity. But both these polynomials actually show up when you study Skein algebras for generic values of Q also, or when Q is a formal variable. They show up in the search for positive bases for Skein algebras. So we have this standard basis that sort of has the simplest diagrams, but it turns out that the standard basis isn't positive in the sense that a positive basis is where if you multiply two elements in the basis, then when you expand it, you get a linear combination of basis elements. And if that linear combination is positive all the time, then you call that a positive basis for an algebra. And so the standard basis for Skein algebras is not positive. But if you look at a standard basis element and you have k parallel copies of the same curve, if you replace that with SK or TK, then you get a different basis that's unitriangularly related to the standard basis, because these polynomials are monic polynomials of degree k. And those have been studied and have been shown to be positive in many cases. So Kepler showed that the Chebyshev, so and these are the S's give you the band's basis and the T's give you the bracelets basis. So Kepler showed that the band's basis is positive for all surfaces except for the torus, and Mandel and Chin showed that the bracelets basis is positive for all punctured surfaces. And Dylan Thurston sort of originated that conjecture and proved it for Q equals 1. And for the torus, it was constructed, the bracelets basis was constructed 25 years ago, just for the torus, and that was the only example known for a while. Okay, so these Chebyshevs are sort of ubiquitous in Skein theory. They show up for generic Q and at a root of unity.
Okay, can I ask you? So you have the TK in the TK case for Q equal to 1. Can you make some comment on spacebar? This is Q equal 1 is spacebar number. How about in general? Okay.
You said, yeah, so Q equals 1 is a special number that gives you this.
Right.
Yeah, so if Q isn't 1, then you'll get some polynomial, but there'll be Q's that don't cancel out, so it won't be an integer polynomial. But you can, so there is a relationship that TK equals SK minus 2. So you could rewrite TK as this picture minus the picture with K replaced with K minus 2.
In general sense, what is the K? I'm sorry, Q is the complex number. What is it?
Oh yeah, Q is a complex number. Yeah, so what I want to talk about more is the Frobenius homomorphism that we had looked a little bit at just making the loop, seeing what the loop should get sent to. So Bonahon-Wong constructed this Frobenius homomorphism for Skein modules in the setting where Q is a root of unity, and n is pretty much the order of Q, but it's Q to the n is either 1 or -1, and n is the smallest such integer, so that Q to the n is 1 or -1. And then T is Q to the n squared, which you want to think of as being 1, but it really could be 1 or -1. And so the Frobenius homomorphism goes from this classical Skein module to the root of unity Skein module. And what it does is, on a link, it threads each link component by the Chebyshev polynomial Tn. And here, this n for Tn needs to match the n up here. And so it doesn't hurt to think of n as just the order of Q as a root of unity, and it doesn't hurt to think of T as 1, but these are the technical conditions to make the theorem true in all cases. And so the original proof of Bonahon-Wong that this respects both of the Skein relations used something called the quantum trace map for surfaces where you can embed the Skein algebra of a punctured surface into a quantum torus, which is an algebraically simpler thing with Q commuting Laurent variables. And over there, like so, in here, there's the easy Frobenius map where you just raise the variables to the nth power. And so they show that that pretty much induces a homomorphism on the original Skein algebra. And then you can get from the Skein algebra of surfaces to Skein modulo free manifolds without much work. But this was a complicated proof that used a lot of machinery. Tangley is given a purely Skein theoretic proof that didn't use quantum algebraic machinery, but it did use the fact that the Skein algebra of the 3 punctured sphere is a polynomial algebra in 3 variables, which doesn't generalize to higher rank. So that's one reason why I'm interested in a different Skein theoretic proof. And this homomorphism, not only is it well defined, but you can use it to construct central elements of Skein algebras, and you can characterize the centers and study the representation theory. So Bonahon-Wong originated that study, and then it's sort of been completed by Charlie Frohman, Johanna Kanya-Berdyshinsky, Tangley, and Jordan Gunev, David Jordan, and Pavel Safronov. And so around 2020 or so, people started looking at SL3 Skein modules and Skein algebras because they sort of completed the study of the basic fundamental properties of SL2 Skein algebras. Okay, so the goal of the talk will sort of be to tell you how to see that this is well-defined map using a new method. Right. So we already saw why this Frobenius homomorphism respects the loop relation. That was the easy relation. But the harder relation is the crossing relation. So we need to see that it respects these sorts of relations. This is the image, like we're looking at an identity that needs the holes for the Frobenius to be well defined. So we have this crossing. I guess I think of the crossing the wrong way, but we remove a crossing and get this linear combination here. But and then we've threaded each knot by Tn. And so if the Frobenius homomorphism is well defined, then we need this identity to hold. But the fact that this identity hold is not obvious by looking at it, because here this is an n degree polynomial, so you'd have to expand that. So the top term has n squared crossings, and we see that if you take all of the vertical crossings, you get something that shows up here. If you take all of the horizontal cross resolutions, you've got something that shows up here. But there's lots of intermediate terms on both sides of this equation, and so those have to cancel out, and it's hard to see that. Okay, so that's the goal of the talk will be a way to see that, and then the fact that you get central elements by using this homomorphism, that's somehow easier to generalize to higher rank. So I've done that with a few groups of collaborators for SLN with Francis Bonahon, for G2 with this RU group a few years ago. and then SV2N with Hyun Woo, and then PGL2, which is closely related to SL2 with another RU group. So showing that you get central elements this way is easier than checking that the Skein relations are satisfied. And another reason that I'm interested in SL2 is because there you can consider webs for SL2 where you have vertices and then edges labeled by integers, and you replace, you interpret this as some linear combination of things that actually aren't webs, but these are Jones-Wenzl projectors that I haven't defined for you yet. But work of David Rose and Daniel Schopenhauer shows that the web relations that these sorts of webs satisfy for SL2 are actually pretty similar to SLN webs. So if we can apply the Frobenius to a web of this type and express it in terms of webs, then that would be progress because we don't know how to apply the Frobenius to a web. And with an RU group, we, for the simplest such web where if you have 1, 2, and 1, then they wrote a computer program to apply the Frobenius homomorphism to that. And so we have sort of a conjecture formula that we can check holds up to if the root of unity is order 6 or less, then the formula definitely holds. Yeah, so we're sort of, even though we know what the Frobenius does to a knot or a link, we don't know what it does to a web, and that's an issue for higher rank things. But even for SL2, you can consider webs for SL2, and we don't fully understand what it's doing to a web in that case either. But so we do know a little bit for higher rank situations. So for SL3, so there are these trivalent webs for SL3, these Kuperberg webs, and the Skein module is actually spanned by links. So, and we know that a link should be threaded by a 2-variable analog of the Chebyshev polynomial. And the fact that it has 2 variables is because SL3 has 2 fundamental representations instead of 1. And the Skein algebra of the ANOS is a 2-variable polynomial ring in that case. So, so we can show that the Frobenius homomorphism for SL3 Skein modules exists, and we know what it does to links. And Kim Kim and Tong Wei and Jiao Wang have further generalized it to a situation involving stated Skein modules, which is, it involves skeins that have endpoints on the boundary. But our proof doesn't tell you what to do to webs, and it's not entirely Skein theoretic. So the idea of our proofs is that you can consider the case of a surface, and these stated Skein modules will allow you to cut the surface into pieces. And this one of the elementary pieces is actually an algebra that's isomorphic to this quantum group OQSLN. And that quantum group has a Frobenius homomorphism associated to it from the quantum algebra perspective. And you can sort of glue together those pieces and induce a homomorphism on the original surface. But in doing so, you don't know what happened. If you had a web on the original surface, now you cut it into pieces and rewrite it as arcs and raise arcs to power and then glue it back together abstractly. So it doesn't give us a way to compute it. So there's not much known about what happens when you apply the Frobenius to a web. But with Hyun Kim and Jiao Wang, we can at least say that for SL3, you have an SL3 web. There is a standard basis, just like for SL2, it involves non-elliptic webs. So trivalent bipartite graphs on the surface that have no, it doesn't bound any fourgons, it doesn't bound any twogons, and it doesn't bound any disks. So that's the standard basis for SL3. So if you take an SL3 web and you apply the Frobenius map to it, you do get integer linear combination of elements. And that's a good sign for these webs being involved in a nice basis, because the Chebyshev polynomials were involved with nice bases, and they were integer polynomials. So so whatever the Frobenius of a web is, it's somehow an integer. It's somehow an analog of Chebyshev polynomials, but it's a non-polynomial thing. So that's these are the sorts of questions that we would like to know, but they're hard, so that's why I'm studying SL2 still.
I'm sorry.
Yes.
Can I ask you a question about, and this is the surface, could you give more detail about the surface on this?
Yeah, the surface for like this guy.
Yeah.
Yeah, so it's any surface. It could have punctures or it could be a closed surface. And then, yes, so maybe the webs for SL3, it's not just curves, it's trivalent. So vertex looks like this or like this, where they're all pointing out. And then, so what we mean by non-elliptic webs is that you don't have any squares or two-gons or loops. So if you, there are Skein relations to get rid of these three sorts of things. And so if you look at what you're left over with, you'll get a spanning set, which actually turns out to be a basis. And so if you took any web on the surface and you applied our Frobenius homomorphism to it, you get some linear combination of webs. And if you rewrite it in the basis, all the coefficients happen to be integer coefficients. Yeah, so it's hard to say things about webs for higher ranks. So the idea is to go back to SL2. And so, yes, so my goal is to find a new purely Skein zero degree to construct the Frobenius homomorphism that has more of a chance to generalize to higher rank than the other ways we know. And we want to try to compute the image of the Frobenius on a web. And so we want Skein identities that are local enough that you can imagine applying them to edges of webs. And we also want to study relationships between Frobenius elements and Jones-Wenzl projectors, because the Jones-Wenzl projectors show up in the bands basis and the Frobenius elements show up in the bracelets basis. And so we'd like to have relationships between them so that if we understand one of these a little bit, then maybe we can use that to understand the other ones and vice versa. Yeah, so more about SL2. So I want to tell you a little bit about the relationship between these diagrams and the SL2 representation category and to tell you what Jones-Wenzl projectors are. So the Temperley-Lieb category in this definition is a diagrammatic category where the objects in the category are non-negative integers and the Hom sets are vector spaces. So if you're in the Hom space from K to L, it'll have K dots on the bottom of the diagram and L dots on the top. And you'll look at all linear combinations of tangles that have that boundary data. And it's okay to have crossings because you can use the Kauffman bracket relations to get rid of the crossings and trivial loops to get rid of those. And so there's a standard basis for the Temperley-Lieb for each Hom space and Temperley-Lieb category where you look at non-crossing planar matchings. And if you look at an element in TL44, it would just be 4 vertical strands. So there's an identity element for each. TLKK is the Temperley-Lieb algebra on K strands. Right? And then in this category is isomorphic to the full subcategory of the representation category of UQSL2, where you only consider objects that are tensor powers of the standard representation. And so here, the functor that gives you this isomorphism would send these 4 dots, the object consisting of these 4 dots to the 4th tensor power of the standard representation. And it would send this whole picture to a morphism between the 4th tensor power and the 6th tensor power. And so that isomorphism doesn't give you the full representation category, it only gives you this subcategory. But if Q is generic, you can get the full representation category by taking something called the idempotent completion of this category. So, so in that case, we would have idempotents would become objects and we'd be allowed to take direct sums And that's how you can recover the full representation category when Q is generic. So the correspondence between this diagrammatic category and the representation category is that the highest weight K irreducible representation corresponds to an element called the Jones-Wenzl projector on K strands inside of TLKK. So each irrep corresponds to a linear combination of diagrams, and that linear combination of diagrams is an idempotent. And so it's called the Jones-Wenzl projector on K strands, and we can define it by axiomatically by these two axioms. So the first axiom is that if you expand the Jones-Wenzl projector on K strands in the standard basis for the Temperley-Lieb category, the coefficient of the all vertical diagram, called K vertical strands, has its coefficient 1. And then the other axiom is that if you take your Jones-Wenzl projector and you have a cap on top of it, you get 0, or if you have a cup on the bottom of it, you get 0. And so it's called the uncappable property. And these two axioms guarantee uniqueness, that if you have two elements that satisfy these two axioms, they're actually the same element in this category. But they don't tell you how to construct it. So for construction, you do it recursively. So Wenzl gave this recursive construction that Jones-Wenzl 1 is just the identity strand. That's the only thing that's going to have coefficient 1. And then it vacuously satisfies the second axiom. And then Jones-Wenzl 2, we construct it using this formula. And we see that the coefficient of the identity is 1, and it's uncappable, because if you put a cap here and here, then this would shrink to a cap, and this would have a circle on top of a cap. But the circle is negative quantum 2, and so we get a cap minus a cap, which is 0. So that satisfies both of the axioms. And then past that, we define Jones-Wenzl K in terms of Jones-Wenzl K minus 1, using this formula here, where we take Jones-Wenzl K minus 1 and then put a strand next to it, and then plus this coefficient, quantum K minus 1 over quantum K, times this picture where we have Jones-Wenzl K minus 1 with one strand that bends up, and Jones-Wenzl K minus 1 with one strand that bends down, and we've composed these. And this is not too hard to show that this will satisfy these axioms. But this formula might not make sense if this denominator is 0. Because so if Q, the 2K is 1, then this denominator would be 0, and that would be an issue. But the recursion shows that Jones-Wenzl K certainly exists if all these quantum integers are non-zero and we can define by them. So if the formula makes sense, then it constructs the Jones-Wenzl projector. But what's sort of interesting is that sometimes the formula doesn't make sense, but then you can actually construct the Jones-Wenzl projector even when it doesn't make sense. So we'll talk about specific values of K, where Jones-Wenzl K exists even though not all the quantum integers are invertible. So in that special case where you're at a root of unity, in our situation that we've been talking about, we have that quantum n is 0, but quantum k is not 0 for k less than n. So quantum n is the first quantum integer that's 0. And so in this situation, if you take the idempotent completion of the Temperley-Lieb category, not all of the Jones-Wenzl projectors exist. So you're not going to get all of the irreducible representations or decomposable ones, but you will get all of the direct summands of the kth tensor power of the standard representation. And those are called the tilting modules. Or it's another way to characterize tilting modules for EQSL2. And so our Jones-Wenzl recursion implies that Jones-Wenzl 1 through Jones-Wenzl n minus 1 all exist because the quantum integers are non-zero up until that point. Jones-Wenzl n won't exist, but it'll turn out that Jones-Wenzl K will exist if K is minus 1 mod n. And Jones-Wenzl 2n minus 1 will be the most important one for this talk, but we'll briefly talk about how to construct the other ones as well. So next I'll tell you how to construct Jones-Wenzl 2n minus 1. So we know that Jones-Wenzl 1 through Jones-Wenzl n minus 1 exists, but it's not obvious that Jones-Wenzl 2 n minus 1 exists because the recursive formula stops working. Right? So, so we sort of have this different formula where we can write Jones-Wenzl 2 n minus 1 in terms of Jones-Wenzl n minus 1. So we see that we know that Jones-Wenzl n minus 1 exists, and we can write down this formula. So this formula makes perfect sense as an element. And Indraneel and I found it independently, but we found that it was in the literature already, which was good. And then, so it's easy to check that this satisfies the axioms. So that the identity coefficient is 1 follows from seeing that we have these diagonal strands here, so there's no identity element coming from those terms. And here the identity element will have coefficient 1 because the identity element of Jones-Wenzl n minus 1 has coefficient 1. And then to show that it's uncappable, you have to put a cap at every spot and see what happens. And so this alternating sum will give you the cancellation that you'll need. You could obtain the same expression for this Jones-Wenzl 2 n minus 1 by looking at that recursive expression with generic Q, and then carefully cancel the denominators of quantum n, which would have been 0, before you plug in Q then equals 1. So it's not an exotic Jones-Wenzl projector. It comes from the standard way. It just happens to exist when it's not obvious that it exists. Because these denominators cancel out. So yeah, so in the Skein algebra literature, these miraculous cancellations, so they're sort of hidden in here somehow. That if you had written out the expression with generic Q, the coefficients of the Temperley-Lieb diagrams that show up in the Jones-Wenzl projector have are ratios of quantum binomials, and the fact that this thing exists is expressing that all the bad quantum binomials disappear. They get canceled out, the things that would have been 0. Yeah, so these Jones-Wenzl projectors, the ones that exist on more strands than n minus 1, and other idempotencies. So these guys give tilting modules, but there are other tilting modules that don't have Jones-Wenzl projectors associated to them. They're constructed in the literature by a few groups of people independently. So Sutton, Telbenhauer, Wedrick, and Zhu, and Martin and Spencer. And back in the 90s, Hyun and Wenzl, they weren't studying it diagrammatically, but they were studying the Temperley category at roots of unity. Okay, so this Jones-Wenzl projector will be the most important one in the talk. Right, and then so for yeah, so our talk won't rely on this fact, but this will provide context for where these Skein identities that we're looking for are coming from. And so, yeah, so in the situation that we're in, that T is T n squared and it's plus or minus 1. So Q to the n is either 1 or minus 1. And in this situation, there's a Frobenius map for the quantum group that goes from the root of unity Skein algebra to the classical Skein algebra. And that induces a functor on the representation categories. And the domain of this functor is just the classical SL2 representation category. So that's the one that if you just study SL2 representations, that's its representation category. And then here is the root of unity representation category, which is the more complicated one. This one's not semi-simple. This one is. But we can plug in our standard representation into this functor, and we get out something in here. So this V upper T just means the standard representation when Q equals T. So the standard representation of the classical universal enveloping algebra. We can plug that into the Frobenius functor. And what you get out is not a tilting module. So there's no idempotent in the Temperley category corresponding to it, because idempotent completion of the Temperley category only gives you things that are direct summands of tensor powers of the standard representation. So we can't depict the Frobenius of the standard representation inside of the Temperley category. There's no way we can draw it with pictures. However, there's this Steinberg tensor product formula found by Anderson and Wen, which says that if you take the highest weight highest weight n minus one module when you're at this root of unity Q, and you tensor it with the Frobenius of the standard representation, you get the module of highest weight 2n minus 1. And so this is an equation where, so this highest weight n minus 1 module corresponds to Jones-Wenzl n minus 1, and the highest weight 2n minus 1 module corresponds to Jones-Wenzl 2n minus 1. So two of the three things in this equation are things that we can depict in the Temperley-Lieb category, because those are just, they correspond to Jones-Wenzl projectors. And this third one isn't in there, but it's at least in an equation where two out of the three things in the equation we understand diagrammatically. So we want to look at Skein identities that sort of look like this equation. And this n minus first Jones-Wenzl is known as the Steinberg module literature. And quantum topologists usually set this thing equal to 0, and then they obtain a semi-simple category after that. But we don't do that in this situation. Right? So so the Temperley category isn't big enough to have the Frobenius module inside of it, but these Skein modules are bigger. So so although the Frobenius of the standard representation doesn't have a corresponding eigencomponent in the Temperley category, it still sort of shows up in the Skein module theory. One of the ways we've already talked about is that if you have a knot threaded by the Chebyshev polynomial, we want to think of that as a Frobenius element, that somehow that came from the Frobenius functor. And then there's another situation in the case of stated Skein modules or molar Skein modules, where if you have an arc, you can apply the Frobenius homomorphism in that situation to the arc, and you just get the nth power of that arc. And so I'm introducing this notation to depict sort of two different ways that the Frobenius elements show up in the Skein theory. So if we have a loop that's colored by green, I want to use that for threading the loop by Tn. And then if I have n parallel copies of an arc that starts and ends at Jones-Wenzl projectors, then I want to consider that as also the image of the Frobenius on just a single strand. So if you have an arc labeled by green, it's n parallel copies of the arc. And if you have a loop labeled by green, it's the nth Chebyshev polynomial threaded along the knot. And so, so our main theorem is these two Skein identities that hold in the Kauffman bracket Skein module. So n is the smallest positive integer such that qn equals 1 or minus 1. And the first identity says that if you have Jones-Wenzl n minus 1 and you have a knot threaded by Tn, you can take that Jones-Wenzl projector and go up next to the knot and then join it up to become Jones-Wenzl 2n minus 1. And the knot that was threaded by Tn now becomes n parallel copies of an arc. And the other identity is if you have Jones-Wenzl n minus 1 and you have n parallel copies of an arc, you can go up to it and you can join it up and get Jones-Wenzl 2n minus 1, and then n parallel copies of arc remains n parallel copies. And so the purpose of our green strand notation is to sort of unify these two identities into one local identity, where it says if you have Jones-Wenzl n minus 1 next to a green strand, you can join it up to get Jones-Wenzl 2n minus 1, and the green strand stays green. So here the Tn loop became n parallel copies, but we color both of these green. So it sort of gives us a more local way to depict these Skein identities. And we view these as incarnations of the Steinberg tensor product formula. That if you have Vn minus 1 tensor for Frobenius of V, you get V2n minus 1. And Vn minus 1 corresponds to Jones-Wenzl n minus 1. The Frobenius corresponds to a green strand. And V2n minus 1 corresponds to Jones-Wenzl 2n minus 1. Right? But we don't know, we don't have the technology to, so we've proven this identity in the Skein module theory, and in the quantum groups literature, this is an identity, but we don't know how to use one to prove the other. because yeah, we just don't. They sort of live in different universes. That this sort of involves all possible representations, and this one only involves things built out of the standard representation. But there should be some connection to be able to. Like these are clearly the same versions of the identity, so we should different versions of the same identity. So in the future, we should be able to connect these up more precisely, other than just saying they look alike. Okay, and so yeah,
Question. What are A and B?
they can be anything. So they just have to have there are any numbers larger than n. And yeah, so maybe to explain this notation, there are other strands here, like A is at least n, and then if there are other strands, I don't care where they're going. I just didn't draw them to make it simpler. But yeah, so A doesn't have to equal B, but they just both have to be larger than n, so that there are enough strands to have n parallel copies.
For example, the sense of the cartoon A and B is the vector space.
No, A and B are labels. Those are natural numbers that, yeah, so it's like Jones-Wenzl A and Jones-Wenzl B, and they have n arcs going between them. But there are other strands that I didn't draw. And so we want to use those Skein identities to see that the Frobenius homomorphism of Bonahon-Wong is well defined. So so we've already considered the loop relation. So the main relation that we need to consider is this: that if we have so when q equals 1, we could, or when we're at q equals t, we could rewrite a crossing as linear combination of the two resolutions of the crossing. But then we apply the Frobenius map to it, and we need this identity to hold in the codomain of the Frobenius maps. That's where q to the 1/2 is q to the 1/2 for HCN squared. We need to see why this identity is true. And so this is just a local picture. So these strands really connect. So this is either a knot or a link, depending on how the strands connect up. And same with these guys. So these are skeins inside of a 3-manifold, but we can consider a thickened surface that contains our skeins. If we can prove the identity inside of the thickened surface, it will hold in the 3-manifold as well. Because if we can prove the identity using less space, then we could have proven it using more space. And we can also assume that our thickened surface is punctured, so we can remove a point from our surface, because that just makes the surface smaller. And so for the same reason as the first bullet point, then if we can prove it in this smaller space, then it holds in the larger space. But this identity doesn't have Jones-Wenzl n-1 in it, like our Skein identities did. So we have to introduce that somehow. And so the idea is we can't just pull it out of thin air, because Jones-Wenzl n-1 closed up ends up actually being a multiple of quantum n, which is 0. But we can close out Jones-Wenzl n-1 around a puncture, and we got our polynomial S2n-1. So it's not 0 in this case, and that's the reason that we wanted to puncture our surface first. And not only is this element not 0, it's not a 0 divisor in the Skein algebra of our surface. And so it's true that there are no non-zero 0 divisors in Skein algebras, but that's hard to see. That took work by smart people. But the fact that this element is not a 0 divisor is easier to see, because if you think about multiplying by a non-zero element in the standard basis, you can just shrink this guy around the puncture so it doesn't actually introduce crossings when you multiply. And so when you multiply by an element, you're really just adding copies of this loop around, like linear combination, these around the puncture. And so if you just keep track of the highest degree terms, there's no way that you can get 0 by multiplying this element by a non-zero element. So since this guy is not a 0 divisor, we can, if we show the following identity, then we'll get what we wanted to prove. So here are these green strands were the strand threaded by Tn. And so if we can prove this identity, then we'll get back to the identity we wanted by, we can divide through by Jones-Wenzl minus one loop because it's not a zero divisor. And then we can fill in the puncture afterwards. And that'll get us to the identity that we wanted. So, and here we can use our Steinberg-Skein identities. So our Jones-Wenzl projector, so this is the left side of our identity. And the Jones-Wenzl projector is an idempotent. So we can take 4 copies of this projector. And then we can send each copy to one corner of the diagram. So we can send this guy over here to join up. And so we're using our Steinberg identity that says you join up Jones-Wenzl minus one with green strand gives us Jones-Wenzl 2 minus 1, and the green strand stays green. And so originally this was a closed loop, and then now it's become arcs. So maybe this guy's a loop or maybe it's an arc. We don't know, but that's why we had our two identities. So we can join a Jones-Wenzl n minus 1 there as well. And so we can do that at all 4 corners of our picture. So the left side of the identity we can rewrite in this way. And then the right side of the identity, we can do exactly the same thing to join Jones-Wenzl 2 and minus 1 to the 4 corners. And so now what we have, it only differs really in this rectangular region, so we can restrict our attention to proving some identity in a rectangle, whereas before this guy wasn't really contained in a rectangle, and that caused complications. And also, these things are no longer polynomials, they're just n-parallel copies of an arc. So we've simplified the situation. So now we're just looking at this local situation where we have n-parallel copies of an arc and n-parallel copies of an arc crossing each other, and they all end at Jones-Wenzl projectors. And it should reduce to this linear combination. And since we're in the situation where we're in a rectangle, people have done this in the literature lots of different ways. And but we have a new way to see this where you can take Jones-Wenzl n minus 1 out of this projector using the absorption property, and then you can join it up to this to get Jones-Wenzl 2 n minus 1. And then you can absorb all the crossings into the Jones-Wenzl projector, because each crossing expands to a vertical resolution or a cup and a cap, and every cap would get killed. So, so using these first steps, you reduce from n squared crossings down to just n crossings. And so, so it becomes manageable after that. So that's how we reconstruct the Frobenius homomorphism, the Bonahon-Wong, using our new Skein identities. And then I want to tell you, so far I've sort of explained how to interpret a single strand colored by green, but that's applying Frobenius to the standard representation. But you could apply the Frobenius to a higher weight representation than the standard representation. So in that situation, we want to think of taking a Jones-Wenzl projector and then applying the Frobenius homomorphism to that. And so we just want to sort of view it as Jones-Wenzl K, but all of those strands are green. So we're in the situation, so you take Jones-Wenzl K, where you're originally at the parameter T, so K equals T, which is 1 or minus 1, and then you apply the Frobenius homomorphism to that. And the green strands, to make sense, they should either end at a Jones-Wenzl projector or end at one of the Frobenius of a Jones-Wenzl projector. So for some examples of this local notation, when K equals 2, is if all the strands end at a Jones-Wenzl projector, then this thing just looks like the second Jones-Wenzl formula. And then, so it just looks exactly like Jones-Wenzl 2. But then if you have a strand that connects back up to the same thick Jones-Wenzl projector, then one of the terms you get will be a loop. And so, so here we had all arcs, but here we have a loop. But this local notation can sort of manifest in different ways depending on how the strands connect up to each other. But it's similar to how our green strand notation was doing originally. And so we can use these thick Jones-Wenzl projectors to describe the other Jones-Wenzl projectors. So Jones-Wenzl n-1 exists automatically, and then 2n-1, we showed how to construct that. So this formula shows how to construct Jones-Wenzl kn plus n-1 for all k. And you're doing it recursively. So we know how to construct Jones-Wenzl 2n-1, and we're making k at least 1 here. And so we just plug it into this formula, and we can show that this satisfies the axioms. So this is Jones-Wenzl n-1 plus kn. And so these Jones-Wenzl projectors were also found in the literature, but their formulas aren't identical to ours, but they all satisfy the axioms. So they're the same elements, but they did it a different way. And so we want Skein identities that involve these Jones-Wenzl projectors that generalize the two that we have talked about before. So the Steinberg Skein identity, or the Steinberg tensor product formula we showed earlier, was if you took the Steinberg module and you tensored with the Frobenius of the standard module, but now we replace the standard module with the highest weight K classical module. And here we have a tensor product formula where you take the Steinberg tensored with the Frobenius, gives us another highest weight module. And here we've taken n-1, and we added a weight kn to it. So for k equals 1, this was exactly the first Steinberg tensor product formula that we saw. And then we have corresponding Skein identities involving these, where if you take Jones-Wenzl n-1 next to a thick Jones-Wenzl projector on k strands, you get the Jones-Wenzl k hat, where k hat is n-1 plus kn. And the goal of these guys is that we'd like to be able to use these to construct or to compute the Frobenius homomorphism on a web, where web's edges would become these guys. But we haven't done that yet. But so if you take a web when q equals 1, and you apply the Frobenius to it, now all the edges look like this. But we don't know what that is in a standard sort of basis. But if you multiply through by the Steinberg Jones-Wenzl projector, then you get something that's expressed in terms of Jones-Wenzl projectors. So it allows you to at least think of the Frobenius, a web labeled by the Frobenius representations, as living somehow in between webs labeled by Jones-Wenzl projectors.
Can I?
Yeah.
Green, K check. Green is a state n-1 strand.
K hat. Yeah, it's
Green case.
yeah. So n-1 plus kn, or the second green one.
Oh,
Yeah. So this guy, it originally had so there's k green strands coming out of it, and you want to think of each green strand as kind of being n. So it sort of is kn. Like when you apply the Frobenius homomorphism to a highest weight k representation,
right.
it becomes a highest weight kn.
Right. Okay. Start with n minus the the pink strand, and then the k is the still n-1 strand, and then now you have to check on k, and then all kind of the n-1 is pink n-1.
Yeah.
So green also n-1.
So there's k. There are k green. So here in this picture, k is 3.
Right. Okay. Yeah, I see.
Right. I think that. Yeah. So thank you very much.